All right, class, welcome to the second lesson in the chapter. So last lesson, we actually talked about exponential growth. This time we're going to look at exponential decay. So our goal is to be able to graph exponential functions that model decay and apply this model to like word problems and applications. So first we're going to compare the difference between exponential growth and decay. So an exponential growth function and decay function both have the same form, which is the form that we talked about last time, which is ab to the c times x minus h plus k. So that form is the same. However, the thing that differs is that for the exponential growth function, the a is positive, so a is greater than 0. And the b is positive. So a and b are both positive, but the b is greater than 1. So like, for example, b could be 2 or 3 or 4. And that's what makes it an exponential growth function. All right, we're going to ignore any reflections about the x or the y-axis. We're only focused on whether the a is positive and the b is greater than 1. And that's what makes it growth. For a decay, has the same form, except now that a is still positive, but b is a fraction that is between 0 and 1. So b is a positive fraction. So for example, 1/2, 1/3, 1/5, 1/6, those are possible values that b can take on for it to be an exponential decay. So we're going to show you how this graph looks like, and you'll see that the decay function is actually decreasing or decaying. All right, so we're going to show you the first example. So all right, so in order to graph this, remember, we want the nice exponents. So some nice exponents include -2, 1, 0, 1, and 2. So we need those nice exponents. So right now we just have x, so we can just plug it in. So when x is -2, -1, 0, 1, and 2. Now we can go ahead and do the math. So we have f of -2. We're going to plug that into the function. So we have 2 times 1/3 raised to the -2. Recall what the negative does. The negative exponent flips the fraction. So this becomes, instead of 1/3, that becomes 3/1. So it becomes 2 times 3 to the second. 3 to the second is 9. 9 times 2 is 18. So this gives us 18. All right, now we're going to do f of -1. So when we plug it in, we get 2 times 1/3 to the -1 power. Flip it and becomes 2 times 3, which is 6. All right, 1/3, so now we're going to plug in 0. So 1/3 to the 0 power. Anything to the 0 power is 1. 1 times 2 is 2. So now we're going to do, now we're going to plug in f of 1. So we have 2 times 1/3 to the first. 1/3 to the first is 1/3. 2 times 1/3 is 2/3. Now the last one, we're going to plug in 2. So 2 times 1/3 to the second. 1/3 to the second is 1/9. So we have 2 times 1/9 is 2/9. Okay, so now we got our numbers. We can go ahead and make the plot. So we have a -2. We have all the way to 18. Okay, so since we have all the way to 18, it's all the way up here. So we may not even have to graph it, but I'll just put a point there, way out there. We got -1 and 6. We have 0 and 2. 1 and 2/3 is less than 1. 2 and 2/9 is less than 2/3. And you can go ahead and begin to graph the function now. So you can see it's growing pretty fast on the left side, and then it's decreasing pretty fast. This is a decay. You see how it's decreasing? So that's a decay function. So now for the x-intercept, well, this doesn't cross the x-axis. Notice that it's approaching the x-axis and it never actually touches the x-axis. So this is the horizontal asymptote at y = 0. So the horizontal asymptote here is y equals 0. There is no x-intercept. It doesn't cross the x-axis because it doesn't cross the asymptote. For the y-intercept, notice that the y-intercept is here, which is a value of y equals 2. The domain exists for all positive, all negative values of x and all positive values of x. So it's negative infinity to positive infinity. For intervals of increase or decrease, this function is decreasing from left to right, if you notice. So that means it is decreasing from the negative side to the positive side. The range, so the range are the y values. So y cannot equal to 0 here. So y is greater than 0 because y cannot be negative, but it can only be positive. You can tell that it's only going up there. So y is greater than 0, or you can say 0 to infinity. For the end behavior, so notice as x goes positive infinity, the graph is actually approaching 0. So as x goes to infinity, y approaches 0. And then when the graph goes negative, so as x goes to the left or negative, the graph is going up like that. So that means it's going to infinity. So this is sort of like the reverse of the growth function. If you notice that these are reversed for growth versus decay. All right, let's look at another problem. So again, we're going to do the graph of this guy. So we're going to plug in, we're going to use these nice values for x. So, okay, so let's plug in -2. So we have 4 times 2/5 to the -2. So 2/5 to the -2, that you're going to flip it. So it's going to be 5/2. Remember that when you have a negative, you flip and forget. So you flip the fraction, so it's 5/2. And then you forget the sign, so now it's squared. 5 squared is 25. 4 squared, or 2 squared is 4. So notice that the 4's cancel, leaving you with 25. Pretty big number. Now let's plug in -1. Again, flip and forget. So flip the fraction, forget the sign, so it's positive. And then now you got to multiply. 4 times 5 is 20. 20 divided by 2 is 10. All right, now let's do the other one down here. 4 times 2/5 to the 0 power. Anything to the 0 is 1. 4 times 1 is 4. Now let's plug in 1. 4 times 2/5 to the first power. 4 times 2 is 8. So you got 8/5. Now we're going to do the last one. 4 times 2/5 to the second. 2 to the second is 4. 5 to the second is 25. So I got 4 times 4/25. 4 times 4 is 16. And again, you can do this on the calculator to make sure that this works out. So now we can go ahead and plug these numbers in. So x is -2, y is all the way at 25. So I'm not even going to bother to graph that because it's too high. Now let's do -1 and 10. That's all the way over here. 0 to 4. 1 and 8/5. 8/5 is between 1 and 2. And then 2 and 16/25, that's less than 1. All right, so you can kind of tell the graph is trying to approach this here, and it is increasing on the left side. All right, so that's your exponential graph. It's a decay. There is no x-intercept because remember, in this case, the graph is trying to approach y equals 0. So that's your HA. So y equals 0. The y-intercept is over here, which is at y equals 4. That's where it crosses the y-axis. The domain is all real numbers because you have all the negative values for x and you have all the positive values for x. For intervals of decrease and increase, it decreases from negative side to the left side, to the right side, sorry. From negative side to positive side, it decreases. For the range, you're greater than 0 here, because the smallest that you can be is just above 0. So 0 to infinity. The end behavior, so as x is increasing, y is decreasing and approaching 0. So as x approaches infinity, y approaches 0. And as x is going to the left or more negative, then the graph is actually increasing. So as x approaches negative infinity, y approaches infinity. All right, so now let's look at another graph, yet another one. So this one's a little different just because you have the transformation x plus 5. So let's write out what that transformation is going to look like. So the plus 5, remember, is going to shift it to the left 5. So we have left 5. The minus 3 on the outside is going to shift it down 3. And then the 4 here is going to do a vertical stretch by factor of 4. Okay, so that's what the 4 is going to do. That's the transformation. All right, so now we're going to go ahead and plug in. So we need, remember, we need this to be -2, -1, 0, 1, or 2. Okay, so the only way we can make it to these numbers is to plug in for x to see if what makes it -2. All right, so if I were to plug in for x, so x plus 5 equals -2. What does x have to be to give me -2 here? Well, x has to be -7. -7 plus 5 is -2. All right, now let's try to get -1. What does x have to be to get -1? Well, it has to be -6, because -6 plus 5 is -1. What about 0? What does x plus 5 have to be to get 0? Well, x has to be -5. -5 plus 5 is 0. What about 1? What plus 5 is 1? Well, x has to be -4. Can you see the pattern here? So it's going by ones. So this right here should be -3. And if you do this, you'll always get some kind of pattern. So now we can go ahead and plug it in. So if we plug it in, we get 4. I'll do it over here. So we have 4 times 2/5 to the, now if we plug in -7, -7 plus 5 is -2. So now we have 4 times, remember, negative means flip, 5/2 to the second. 5 squared is 25, 2 squared is 4. So 4's cancel, 25 minus 3 is 22. All right, now let's plug in 6. If I plug in -6, then I'm going to get -1 as an exponent. Flip it, so 5/2. 4 times 5 is 20. 20 divided by 2 is 10. 10 minus 3 is 7. Okay, and you could do that on the calculator if you want to verify. Now let's plug in -5. So we have 4 times 2/5 to the -4 plus 5, or -5 plus 5 is 0, so 2 2/5 to the 0. Anything to the 0 power is 1. 1 times 4 is 4. 4 minus 3 is 1. Now let's plug in -4. So 4 times 2/5. If we plug in -4, we're going to get 1 for the power. 4 times 2 is 8. 8/5. So we have 8/5 minus 3. So 3 is the same thing as 3/1. You need a common denominator here. So I need to multiply this by 5. 5 times 3 is 15, right? So I'm going to get 15 over, and 1 times 5 is 5. 8 minus 15 is -7. So I get -7/5. Again, you can do that on the calculator and get a decimal. Now let's plug in -3. So we have 4 times 2/5 to the 2 power. 2 squared is 4. 5 squared is 25. 4 times 4 is 16. So you have 16/25 minus 3. If you were to do that on the calculator, or just do the math, you would get negative 59 over 75. All right, and if you want to know how I did that, 3 is the same thing as 3 over 1, so I need to multiply by 25. So 3 times 25 is 75. So we get 75 over 25, and then 16 minus 75 is 59, negative. So that's how I got that. All right, now let's go ahead and plug it in. 22 is too big of a number, so I'm going to skip that one. Let's do negative 6 and 7. So negative 6 and 7. Negative 5 and 1. Negative 4. Oops, I thought that was a negative. So negative 5 and 1. Negative 4 and negative 7/5. So negative 7/5 is a little bit past negative 1. We're going to need some more room here, so I'm going to extend this a little bit more. All right, so we got negative 2 here and negative 3. So at negative 3, I'm going to get between negative 2 and negative 3. So it looks like the graph is trying to approach negative 3. All right. So based on the graph, it looks like it's trying to approach negative 3. So that means that negative 3 is my HA. So y equals negative 3. Now a hint for this is you can use this value, and that value will tell you what your HA is. So if there is no number there that you're adding or subtracting, then automatically the HA is 0. If that number is negative 3, HA is negative 3. If it's positive 3, HA is positive 3. So that number will tell you what it's trying to approach. So that's an easy way to determine that. So just a little tip. So here the asymptote is y equals negative 3. So here we have a y-intercept and we have an x-intercept. So we have an x-intercept over here, but we haven't shown you how to do that. So we'll do that in another lesson. So x-intercept, there is one x-intercept, but we will not determine that x-intercept in this lesson. For the y-intercept, we can actually determine what that is. All right, so we're going to plug in 0 in for x. All right, so let's plug in 0 in to x into the function. So if we plug in 0, we get 4 times 2/5, 0 plus 5 minus 3. So 0 is x now. So we got 4 times 2/5 to the 5th minus 3. So 2 to the 5th is 32. So this is 4 times 32. 5 to the 5th number is a pretty big number, so I'll do it on the calculator. 3125. And you can get a decimal for this, since this is a rather large number for the decimal, or for the denominator. So when I do it on the calculator, I get negative 2.96, just about. All right, so that's where it's trying to cross at negative 2.96. So y equals negative 2.96. So you can do that on the calculator. All right, for the domain, it's all real numbers. So negative infinity to positive infinity. For intervals of increase and decrease, it's only decreasing. So it's decreasing from the negative side to the positive side. For the range, the smallest the range the y can be is negative 3, and it can't equal negative 3, so it's greater than negative 3, or you can say negative 3 to infinity. For the end behavior, so we're going to need some room here, so I'm going to erase this real quick just to give myself some room. So as x approaches infinity, positive, y is approaching negative 3. So as x approaches positive numbers, y is actually going down to negative 3. As x approaches negative numbers, so as x goes here left, the graph is going up. So y approaches infinity. Okay, so a very involved problem, but that's how you work it. And that's how you determine all the characteristics. So now let's look at the parent function. So what's the parent function for this guy? Because this guy was transformed, right? So the parent function for him is just simply going to be the base raised to the x power. The base is 2/5. So the parent function is just 2/5 raised to the x, nothing else. And that's the parent function. Remember that the 4 just vertically stretches it. The 3 shifts it to the left, to the right, or down, I'm sorry. The 3 shifts it down, and then the +5 shifts it left. So everything else is just a transformation. This is the parent function. All right, so now we're going to determine whether these functions are growth or decay. So it's really simple. Remember that if the b is greater than 1, so the base, if the base is greater than 1, it's a growth. If the base is less than 1, then it's a decay. All right, so in this example, b is equal to 3, and 3 is bigger than 1, so that means this is an exponential growth. Very simple, right? So in this case, b is 0.6. So b is 0.6, which is less than 1, so that means we have an exponential decay. All right, this one's a little tricky because you have a negative on the exponent. Remember, negative means flip, so you're going to flip it to 1/2. So we have 3 1/2 to the x power. So flip and forget. Now we know that the b is 1/2, and 1/2 is less than 1. So this is really just a decay in disguise. All right, this one's pretty easy. b is 6, which is greater than 1, so this is an exponential growth. All right, very simple to tell whether it's growth or decay. So now let's look at an application. Remember the last time we did this, it was an exponential, so this should say decay, not growth. So make sure you change that to decay. So we'll change that now. So that should say decay. All right. So whenever we did growth, we had a growth factor. This time we have a decay factor. Notice that the formula is very similar to the growth one. The growth one looks like a times 1 plus r to the t power. For the decay one, you're subtracting because you're going smaller. All right, so remember, a is the initial, r is the rate, and t is the time. So let's look at the example. So there are 40,000 homes in Turdville. Again, a made-up town because we're dealing with septic tanks. So 40,000 homes in Turdville. Each year, 10% of the homes are expected to disconnect from septic tanks and connect it to the sewer system. Write an exponential decay model for the number of homes that use septic systems. So this is my my initial amount of homes, and then it's saying 10% of homes are being disconnected. So that means the number of homes is decreasing, right, by 10%. So this is my R. My R is 0.10. So that means our model is y of t equals 40,000 homes, 1 minus, since we're decaying, so we're decaying by 10% every time, raised to the t, so that's the time. In this case, they don't really tell you if it's years or anything, but we know that there's some kind of time involved. All right, so we got 40,000, and then this is going to be 0.9, because 1 minus 0.10 is 0.90 raised to the t. So that is my final exponential model. So then if they said, you know, after X amount of months or years, then you what is the number of homes that are connected, then in this case you would plug in whatever time is. All right. So for number 7, this is the last problem. So this is actually a depreciation problem. So when you buy a new car, or when you buy any car, you have a certain value to it, right? The value that you pay for the car. So let's say in this case you got a car that's $23,000, a Mercedes-Benz or whatever car. Now this car, since it's new or relatively new, will have a value that decreases every time. So as soon as you drive it off the parking lot and you put mileage in it, the value decreases. That's known as depreciation. So that's modeled by a decay because the value is decreasing. So it's saying that the value decreases by 15% every year. So that's my R. So my R, and I'll write it up here. So my R is 0.15. So basically we have, and then this is how much we start out with the cost. So we have Y of t, we have 23,000, 1 minus 0.15 to the t power. All right, 1 minus 0.15 is 0.85, so that's going to be my new model. Y equals $23,000 times 0.85 to the t power. And you know that this is less than 1, which means it's a decay. So that means the value of the car is decreasing, it's depreciating. So we're going to do the graph. So we're going to need a calculator in order to plug in some numbers here. So let's do a quick XY table. And we're going to plug in, 0, 1, 2, and maybe 3 and see how the graph looks like. So if you plug in 0, you're going to get the initial value of the car, which is 23,000. If you plug in 1 on the calculator, you're going to get $19,550. So it decreased a lot over the 1 year. After 2 years, it decreases to $16,617.50. Then 14,000. Then about 12,000, and so on. So I'm going to go ahead and plot that. So 0, 23,000 is around here. And then we got after 1 year, 19,550. After 2 years, 16,600. After 3 years, 14,000. After 4 years, about 12,000. All right, and I'm going to continue the pattern. I'm going to just go ahead and calculate the next one. The next one is about $10,000, a little bit above 10,000. 8,600, 75, so around here. It's actually closer to here. Next is about 7,300. About 6,300 almost for the next one. A little over 5,000. And a little over 4,500. So the value decreased quite a bit. So after 10 years, it went from a brand new $23,000 car to a car that is roughly $4,500 after a decade. So that is depreciation. And notice it's an exponential function. So at some point, it'll level out, right? So that's an exponential decay. So what's the value after 3 years? Well, we just found it. It was $14,124, just about. What happens, what time are you going to have half of the original value? So half of 23,000 is about 11,500. So about 11,500, that's, you know, this right here is 12,500. So 11,500, yeah, it's around probably, you know, around here. So probably about 4 years. Can you see that? That's about 4 years. If you trace it down to the x-axis, that's about 4 years that you can tell. So, you know, when t is about 4 years, you'll get half of the original value. All right, and that's it, guys. That's exponential decay. Those are some applications, and that's how you graph them, these exponential functions. All right, I hope you you know, you got the lesson. Just keep practicing, and I'll see you guys next time.